Hello, everyone. First of all, thank you so much for the invitation. It's really a pleasure to be here and especially to talk to you about this project that we have been working, me and this incredible team that is down below, because it's not only me, but it's really great to have the opportunity to work in this project for the past 3 years now. And I'm going to tell you how PCD-AID, which is the tool that we have been developing, can be a good machine learning tool to diagnose PCD or to help in the diagnosis of PCD. So, but first of all, it's impossible to talk about PCD without talking about motile cilia. And motile cilia exist in many places of our body, but today we will focus on respiratory cilia. And respiratory cilia are important to sweep all those nasty little things that come into our airways and to keep our airways clean and our mucus flowing. So if we don't have this cilia working as they should, this mucus will build up, and the mucus is an incredible good environment for growing of pathogens. So it kind of leads to a catastrophic symptomatology. So when we know now that when we have motile cilia impaired or defected, it can lead to a panel of phenotypes. But today we are going to ignore a little bit of the other ones about hydrocephalus, infertility, organ laterality. We're going to focus on chronic respiratory problems and rhinosinusitis and hearing impairment in these patients. And here is where we talk about PCD, primary ciliary dyskinesia. This is where all these symptoms are more major. This is where they are more felt by the patients. To do a diagnosis of PCD, it's a multisystemic disease, and to diagnostic directly, we need also a multi-variety of tests. So in this case, we need dynamic tests, we need structural tests, we do molecular tests, and for that we need a brushing. And then a nasal brushing is done, and it's usually done in the turbinate using a little brush. With this brushing, then we can do electron microscopy, extracting material, fixing it, and looking at sections of cilia, in this case, cross sections of cilia. We can also do high-speed video microscopy using a fresh sample and then a microscope equipped with a special camera that records these videos and that slows them down so we can analyze the beating pattern and also frequency, and to do, for instance, immunofluorescence as well, looking at these markers that might be impaired in PCD and using some fulcrums and some colors, see if they're present or not, and also genetics. For this, we don't usually use a nasal brushing, but a blood sample. And we know now that more than maybe 50 genes are involved in PCD at the moment, so this makes this disease highly complex. However, electron microscopy is still kind of a very important test for PCD, because it's very sensitive, and we can see a lot when you look at a cilia using electron microscopy, especially if we look at it at the cross sections of cilia. If we look inside the cilia, cilia are air-like structures. When we cut them, we can see inside, and this is how they organize. They're very conserved organelles, and we call them in this organization 9+2. It means that we have 9 microtubule doublets and a central pair. It's a characteristic of a motile cilia. And just as a quick reminder, these little 8s are the microtubule doublets. Then we have the inner dining arms here, more closer to the center of the cilia. And then we have the outer dining arms which are little arms protruding from the doublets, but in a more exterior part of the cilia. We have the radial spoke that is here. We can see a little bit here. It's quite tricky to see, but it's very important that it's there. Otherwise, the cilia will just collapse, because it works more or less like a skeleton of the cilia. And then we also have the Nexin links, which are going to be here holding all these doublets in the right position as a kind of a circle. And this is the main components that we are going to focus on, because if these components are not here, if we don't see them using electron microscopy, it might translate into a genetic defect, meaning has a genetic mutation, that component is not there, and that will lead into a defect that you can see in an electron microscope, and also we can see, you might be able to see that defect translated into a beating pattern. So it's very important that we know that all these components and how they organize in the cilia. So we know that we know all the components now, how they look in a normal cilia, and now I'm going to show you the common PCD defects. And I have here absence of outer dynamics, where the outer dynamics are not present, or at least they might not be completely present, might be a bit stubby, or just a remain of a central or of a outer dynamic there. We have absence of inner dynamics, which is this case over here, a bit more tricky to identify. Then we have absence of both. We have disorganization of the axoneme. So if the cilia gets this very disorganized, crumbled appearance, and then we have central pair defects. In this case, we have a classical absence of a central pair. In this case, we have this sneaky doublet just going into the center of the cilia. It might resemble like a central pair, but it's not. We call it a transposition defect. Then we have defects that are more likely to be secondary defects. We have presence of extra tubules. Sometimes a doublet is replaced by a single tubule. We might have, for instance, a central pair is only one tubule. This is very uncharacteristic. And we have the compound cilia, which is very common in secondary defects and infection. So knowing this, we thought, so if we know how to identify these defects, and they're fairly well conserved between cilia, why not using a machine that we can teach with these defects, with this normality versus abnormality, and see if it can learn, if it can give us a good prediction of a normal versus an abnormal cilia. So to do this, we started by having full images containing several cilia, images collected in an electron microscope, and we started by detecting cilia. So to detect cilia, we in a detection project, basically we are teaching the machine what is a cilia, how does it look like, and for this we just draw boxes. We draw boxes around cilia and say this is a cilia, this is a cilia, and so on. And for this project, in this case, it has different colors, but let's just ignore it. We are just detecting cilia. Cilia that might be normal, abnormal, cilia that might be a little bit tilted, but they are still identified as cilia. Then the work comes after that. So what we need to classify those cilia that we just cropped, that we just squared around, into a classification category, a label. We call them labels. So we can create the labels that we want, A, B, C, 1, 2, 3. We decided to create labels abnormal, normal, and useless. And a useless label, it's sometimes people giggle a little bit because it's kind of, well, it's a bit harsh to call something useless, but that's what they are. When we cannot use them to make a diagnosis, they're basically useless to us. When you are in the microscope looking at a bunch of cilia, we as humans, we just ignore them. We don't even look at them, but the machine needs to know what to do with them because they're there. They're still identified as cilia, but they're useless. So we tell the machine, okay, so just label them as useless. And this is what we've been doing. We've been working for a whole year and teaching a machine what is what. And what you see here going through, and if you look at the corner, you see like a little label appearing. And the pink, it's no abnormal, blue, it's normal, and yellow is useless. And this is just streaming in a circuit, kind of a circuit. It's all like just running, but you can see that it's already giving some predictions after the training, and it has here valid, invalid. It's allowing me to validate its suggestion, its guessing. And this is how we do the training. This is how we do this validation. We just give it material. We ask it to train. After training, a model is created. And this model is used to analyze other cilia that we might upload after. And then the machine with that model will say, oh, wait, I know this is abnormal. And I can say that's valid or invalid. I can accept or not accept. And this is how the training is done. So this is how our overview of our images of containing several cilia. All the yellow boxes are cilia detected by the machine. This is not a training that I did. This is a suggestion made on the machine, detection and classification. This is fairly good. So we have all cilia were detected. This one was ignored, but it's well. It's very, very not kind of classical, but all the other ones were put a square around it. And you can see the blue labels are normal cilia, the pink are abnormal cilia, and you cannot see it in this magnification, but the system actually got it right. All the yellows are cilia that are either too close to the cell and they are just very proximal, so they don't have exactly the components we are looking for, or they are tilted or fuzzy and out of plane, and we don't usually analyze those. But this is how it would look. Here we can also see on the side is our media, it's our images, and I know that this image here has a green little sticker. It means it's trained, but this image here, it still needs to be validated. So I still need to go there and check if the system is giving a good prediction and validate it. And only when I validate it, it will switch to green and it will account for training. So the training will be intercalated with new data and old data, and this is an ongoing process. So machine learning, it's great, it works really well, but it has something that people sometimes talk about, which is the black box. We are working in a black box. And what does this mean? It means that we don't really know what's going on inside. We know what it's giving us, but we don't really know how is it processing the information. And sometimes, just out of curiosity, when you start giving it images, sometimes you forget to crop your images, and your images have a label, like a little the identification of a patient. So that means it's kind of some writing on the image. And then you start training, and you suddenly see that a group of images start being grouped together, but not because of a feature of your cilia. It's because it's focusing attention on writing. So the writing is the only thing that is completely in common in all images. So it will be lazy, and it will give priority to the thing that it's more strikingly different, like similar in all the images, which is the writing. So we have to be careful to things like this. But this is kind of what we see inside the black box, and sometimes it's a bit too late. We already invested so much time. So how can we know what's going on inside the black box? How can we know if the performance of our machine and what our machine is doing, it's what it's supposed to do? So we have something called the attention map, or yeah, it hasn't maybe called the heat map as well, but we call it the attention map. So it's basically a tool that we turn on and we have a small heat map that appears around something, and we know that at least it's there, that the system is putting its attention, it's focusing on that. So if you have that little writing with the patient details, well, that's easy to cut up and to catch and see that it's basically just not going in the right direction. So the attention map is really good to have a sneak peek inside the black box. In this specific case, the machine is telling me, okay, Andreia, this is a cilia, I'm 87% sure, but I'm also 92% sure that this is an abnormal cilia. And I look at the cilia and I think, well, you have to tell me more. I don't understand why. It looks like a fairly normal cilia to me. So when I highlight and I turn on the heat map, I see that the machine is putting attention to that little structure in the middle. And when I look at it, it actually misses a bit of a protrusion of the central pair. The central pair is a bit denuded around. If we look here, we have a normal cilia, and you see that all these protrusions can be seen. And in this cilia, we have a bit of a gap there. And this, it's possibly, I always like to say, just possibly linked to, for instance, a hiding mutation where part of that protrusion, it's not existent. So this is a very subtle defect, and this is a defect that is not easily picked up by eye, not picked up by the human when it's doing the analysis. But it's good to know that the machine was able to pick it up and say it's abnormal, and actually it just represents, using the heat map, where is it not thinking, but analyzing it as abnormal. Where is it putting its attention to? Okay, so now I want to wrap up just showing you how does this validation part is done. So it's kind of just giving you a tour through what I would do. This is just basically a recording of me going through my images. These are cilia that are already cropped, and here I can see that this cilia was suggested abnormal 97% and autodynamic defect, and I'm just basically just accepting it because this is true. That one was abnormal, useless. This one is normal, and so on and so on. And this goes forever again. Another one is telling me this is abnormal, and now to 99. And I just forgot to say something. This was our next step. So we thought, okay, since the system can actually detect that little absence around the central pair, can we teach the machine to identify defects? And this is what we've done with this second project. We are not just focusing on abnormal and normal and useless. We are keeping those labels, but we are then subclassifying our abnormal into a type of abnormality. And this is what we have here. So the machine now is trained with around 8,000 images of cilia from 8 different, 1, 2, 3, 4, 5, 6, 8 different labels. And I've been training them, and now the machine's already giving predictions that are, with regards to the autodyne is always very sharp and quickly to identify it, because the autodyne is something that is very reproducible by cilia, from cilia to cilia. But when we come to defects like disorganization of the microtubules, or central pair defects, or even, for instance, extra tubules, then there is where the machine cracks a little bit, because it's the variety inside the defect, it's so big that sometimes the machine struggles to find a pattern that can correlate with. So this is obviously overcome. I'm going to tell you why, but I can disclaim it's with numbers. We just need loads of cilia, and more of the cilia that actually are trouble cilia, which are these that have defects that vary a lot inside their category of defect. Okay, so as I already said a little bit, and this is what it comes from, this is it's a bit of a subjective analysis. And sometimes even deciding between a useless and a normal or abnormal cilia, sometimes it might be a question mark. It might be, okay, is this a cilia good enough for me to analyze? Sometimes it doesn't even have to do with the defect, just thinking, is this cilia a good cilia? So this is it's quite a subjective analysis. And in all subjective analysis, we need to find a strategy to overcome it. And for that, I want to give you, some of you probably already saw this slide. This is a slide that I really like, and it's very illustrative. When we're working with machine learning, and even if we think about the human brain, when you look at the image like this, we know that there's something wrong here, that this is mops versus dogs. And some of them in the beginning, you might think, okay, this is all the same. But when you start paying attention to little details, you will understand that some are dogs and some are mops. But for the computer doesn't have a brain of the human being, and computer wouldn't look at, oh yeah, I can see a little kind of little nose of the dog or something like that. No, the machine needs a lot of mops and needs a lot of dogs, and then it will start to recognize some features in dogs and some features in mops that will take it to be better in its learning and then in its performance. So the same thing happens with cilia. We have cilia that are a bit more fuzzy, we have cilia that are a bit dirty, we have cilia that are perfect, we have loads. So we have to give the machine a lot of everything for the machine to have enough material to make a correct assumption of. And well, this is kind of always a big question about how is it going with machine learning. And again, just a last cartoon, I promise. We are always worried about how AI will take over us, but well, sometimes this happens. So we do need a lot of material to train it, but still, it's always a bumpy road to go. And even when the results are really good, we sometimes have some situations that go a bit weird. But for this, and to there was another thing that we can do, and now I'm going to show you another strategy that I found to just, I talked to you about the numbers of cilia that we put, but there's another thing that we can do to see if our machine is doing well. And one thing is auditing the machine. We have to audit it, like the same way you would audit between centers, you can audit the machine. So here, what we did, we gathered like 600 can put it to here. We gathered 600 images and we asked 5 cilia experts to look at all of them. In between these 600 images, there were 2 genetically confirmed cases, but we didn't say anything. We wanted to keep it completely unbiased and completely blind. We also gave this 600 images to the computer and we used the model to analyze it. And then we compared everything. And I don't want to completely bore you with these graphs, but I can tell you that we had more than 70% agreement between the experts and between the experts and the AI. Actually, there was one case, it was inner dining arm defect plus disarrangements that the machine picked up 100% of the inner dining arm missing, and the experts were a bit more cautious. And we know this because we as humans, we sometimes question our own performance and our own, what we are seeing, and we try to be too rational. And or maybe there's an inner dining arm there. I just don't want to say that it's not there. It might be there, but the machine is very objective. Oh, it's there or it's not there. So it kind of ends up picking up all the defects that were regarding the inner dining arms, and this was very interesting and made us really happy. And again, we had a very high agreement, and now we are also auditing. I don't know if I have. We are also auditing our other project, the one that classifies into defects, and that one is more complex. In that one, we need a bit more analysis, but I can tell you, despite the fact that the agreement in some defect classifications is a bit lower, it's still very high. It's still very similar to what we see here, which is very optimistic, taking into account that that project is still ongoing and we still have to give it more images and more numbers. Just for you to have a reference, we have at the moment around 700 cilia with outer dining arm defects, and we have 71 cilia with transposition defects. So this is unproportional. The only thing that basically saves the day is that transposition defect is very characteristic. It's something that is very conserved between cilia, and the machine picks it up really quickly. But we still have to have more numbers in extra tubules, single tubules, everything that's more secondary, a bit all over the place, the machine will struggle a little bit more. So, but we learn from this experience of auditing our peers as well, that this is where sometimes we also kind of discuss a little bit more. So it's not completely random. Okay, so no, machine learning and AI in this specific case not going to replace anyone. We see it as an extra member of the team. This is a human in the loop analysis. So we basically fit it with our images. It will give us a result. And we can quickly scroll through the images and see if we agree or not. And this takes minutes against hours that it might take with a normal diagnostic path. So it's an additional member to the team, and it's very it gives us time to do other tasks and to focus on the PCD cases. Those are the ones that really need more attention, and we have time to just focus on those and analyze them with extra care. So we are already using this tool alongside our MDTs. We recruited more than 170 patients so far to go through the BEAT-PCD, and so far I would say the success rate of getting it right, and when I say getting it right, is matching what the expert says. So the expert does it in the microscope, and then I'll do it in the NOUS, and then we compare the results, and the results always match. Sometimes NOUS is a little more sensitive to some subtle defects. It's very sensitive to abnormalities, but that's not necessarily bad. So that creates some awareness for us to look at the cases with a bit more, a second time maybe. Okay, so what's next on BEAT-PCD? Where are we? What we want to do more? But first, what are the advantages? So, sorry, it's just. So we want to reduce the diagnostic turnaround time, and this is obviously one of the major goals. This will lead to also saving money and give a patient a quicker result, which is always good. If we think that it may vary from person to person, from case to case, but everyone would agree that doing an analysis in an electron microscope may take hours. It depends on the patient, it depends on the sample. The sample might be too sparse. If it's a very good sample, it might be fairly quick, but it's always a time-consuming task. And for the machine, if we have the images, it takes minutes. And it's very important when I say if we have the images, and I'm emphasizing this because obviously it takes time to collect the images, but that's why we are in parallel trying to create a way to acquire the images in the microscope in an automatic way. So automatization is the key. So many microscopes nowadays are equipped with softwares that do this automatically, and this might be the future, and might be very the key to do it even faster. And no, we're not trying to make people obsolete. Again, it's just giving the experts enough time to analyze the cases that really need an extra look. Another thing is, and we talk about this a lot, which is we're never judging anyone's capability of analyzing a case. But as a human, if you have 5 cases today, and the day after tomorrow have an MDT, you sure want to have them all done. And your attention span when you start with your first case will not be the same when you start with the last case. Actually, your last case, you might be already looking at your watch, and that no one can be blamed because of that. It's just a human factor. And so it has kind of a curve. You achieve your personal best, and then you just go maybe a bit down in your attention span. And I'm not saying that patient will be misdiagnosed, but you might miss 1 or 2 subtle defects that might be taken into account. And for the machine doesn't happen. The machine has the same attention span, first case and fifth. And this is a good tool for then the expert goes to those images and to those results and can focus in the ones that the machine flagged, saying, well, maybe you should pay more attention to this patient because I thought had like 27% of abnormalities. Okay, maybe good to look through these images and see how it looks. So this is how it would be. Again, I basically already spoke a little bit of improved detection of subtle defects because of its very objectivity of analysis. We know this regarding innodyne arms, central pair defects like hidden, and this is something that might be a good advantage. And it would even give confidence to people that are starting doing the analysis of PCD using electron microscope, because you don't need to know everything when you start, you just gain your experience. But if you have a tool that can help you and guide you through, it might be a good value. So we are also constantly training and auditing. As I told you, we train it, we audit it against peers, against colleagues, and see how it's going. And obviously, this is something that we aim to roll out to the other centers and have them equipped with the model expectedly, so it can be used to analyze their cases. And this is a phase that we are entering now, and this needs validation, and it's ongoing. Another thing that it's ongoing, and it's very fortunate, is the new project that we have is also, I'm just putting it here, it's on like 3 slides, but I want to talk to you about it because this project is rolling, but it's slightly different, but it's using the same AI platform. It's still using the same machine learning that we're using for the electron microscopy images of cilia. But in this case, we are trying to use the machine to identify patterns in beating in high-speed video microscopy. And this might sound a little bit more challenging, and if it sounds, it's because it is, but it's also more rewarding because this analysis, as we all know, it's quite subjective, and it might lead to sometimes some not say discussions, but we can have like disagreement in how does a case look like, but we want to see how a machine would look at these cases and how easy it would pick up these defects. And why are we doing this? PCD is a great model disease to use videos because all the patients that come to clinic have a nasal brushing, and each nasal brushing generates in a routine setup at least 10 videos. So we also know that in PCD, genetic mutations defects will lead to a different beating phenotype. Might be static, might be low amplitude, like the movement of the cilia is not complete. It might be twitching, it might be static. I already said static, but it can give you a wide range of defects. So it's good to see how the machine reads through these difference in pattern of beating. We also have some patients that, for instance, CF patients or bronchiectasis that have videos, and these can be used to train a machine as well, and to see how different are these videos from the ones PCD, how different are these videos from a normal patient, and we can train it as well because we have this data, and it can be used for also for future, for other projects that we might be interested, something else that we want to look at. And this is our new project now. So I'm going to show you how it works. So we have here beautiful, this is how our data set will look. We have a beautiful video of a apparently normal ciliary beating. And what we need to do, we need to transform this video, which is kind of this gray, black, white color palette, into a more happy color palette. We needed to have colors, and this colors into basically translate the movement of the cilia and the beating pattern and the speed. And this is things that we can measure, but not only that, the machine will use this optical flows images to train. And this is the type of material we will give our system to train with. We're not giving it this anymore. We're just giving this type of material. And we are doing this using a Python script. So how is the project's designed so far? I thought in the beginning that we should separate primary brushings from cell cultures, which sounds reasonable. However, we don't have those many cell cultures and numbers. We already spoke about numbers, and numbers are important. So we're just going to focus in mixed brushings for now, and then later on we can create multiple projects. So we can create another project where we separate these two type of brushings. But for now, we want to see how the system behaves in identifying PCD versus non-PCD, and if it actually learns from this material, because not all PCD videos will be static, and not all non-PCD videos will be normal. So we want to see what type of model and how it behaves, what is the performance. At this point, we are also separating top views from side views because they're very different and the system will struggle. So these will be two separate projects. We'll have project with top view PCD non-PCD, side view PCD non-PCD. Okay, so this is how it looks so far, very preliminary. So same setup as you can see, but now we have video. So we click on the video, immediately opens all the frames of the video. We can play it. This video was classified as PCD, as the next one as well. And I want to call your attention is the fact that we have a big block of color, but we don't see any specific movement, like wavy movement or organized colors. The next movie that I'm going to put here, it's a non-PCD movie. And here you can see that the color, it's going to be more focused in the border where the cilia are. So this is the kind of training, the material that is used to train. And in here, we don't detect anything. We just immediately classify the videos into PCD or non-PCD. And just as a kind of a result of our preliminary data, you can see that healthy subjects will have a rather dark image, and the only thing that you will see are the cilia beating, because the cilia are the thing that beats more in that image. It has more movement, so it will be picked up and colorful. But in the video where we have a static sample, for instance, the color is in the cells, because the cells kind of move slightly in the video, and that is where it's going to be picked up. It's not really the movement of the cilia because they don't exist. With regards to rotation, this is something a bit more tricky, and we really cannot differentiate from this image, but this is something that's going to be trained as well. So we expect to look in the top views to be able to identify a movement of rotation as an abnormality and related to PCD. Okay, so this was what I wanted to show you today. I want to thank everyone that has somehow helped with this work. All the people that are in the list of authors, obviously, but people in the lab, Ranjit and Farine, from Cosmonio now, Intel, Eugene, our engineer, have been a great help to navigate this AI, and Mr. Helmut Ganegi from Diatom provide us with a knife to do our sections. And to you all for listening, and I hope you enjoyed it and that I'm available to answer any questions.
Thank you so much, Andreia. Really exciting talk. And I think you'll be pleased to know that the general consensus in the chat was that everybody loves the cartoons. So we continue to use those. So I'll kick off the Q&A session while people are thinking of some questions to pop into the chat. Just a practical question. So when you plan to roll this out to other centres, different machines for TEM, are they all able to collect the same resolution of images?
That is such a good question, Katie, and I was hoping someone would put it. It's really important that we figure this out. I still can't answer you that. I know that we have 2 different microscopes in the lab today, and they give different images because one is equipped with a weaker camera, low resolution camera, and we know that the images are not as good, but the system is still able to pick up. My rule, and I'm very optimistic regarding this, I do think if in your service, you as a human can look at your cilia and pick up the defects, there's no reason why the machine won't be able to do it as well, because they have to be there. If you can see them, if you have enough resolution for you to make an analysis, there's no reason why the machine cannot do it. But for this, we need to enter this kind of beta phase where we receive images from our partners and we will trial them. And then after that, this is when we're going to say, yes, we're good to go. But this is the first phase, is to see if their images collected in their microscopes will give the same performance as we're having now. This is it.
That's great, thank you. And just another question of mine, also with the rollout, would the scientists have to put the images into NOUS, or would it be something like a plugin that you'd use in ImageJ, for example?
So there are some options. Obviously, the center can have this setup, can have a big computer, a big server, can have NOUS, but the outcome won't be, so your analysis won't be done in NOUS. NOUS is a training platform. So they always need a different tool to do the assessment. We do it here because this is the platform that we have with training, and we are extracting the data in a very kind of IT way. We're just extracting it, but it's not kind of optic of the user kind of way. So they would have a more user approach, but the best thing is that we can actually extract the model. The model can be extracted, and you can put the model in a web interface. For instance, it can be on a web. You can have it on Google. You can enter with your password, and you can use it. You can just upload your images, and the model would do it for you. So you don't need to worry too much about having this software and having it working in your computer. You have something as simple as just clicking a link and be able to, a bit like, I don't know if any of you know of AI Experiments. It's a tool by Google that is basically just a lab for AI, more for youngsters, but it's pretty cool to use. And basically you can go there and play a little bit with 4 images of cats, 4 images of dogs, and then see if you look more like a cat or a dog, which is basically what it does. It's really basic machine learning. It's how this works. But again, you wouldn't need to have the big setup. You can just have the model with a few megabytes maybe, and just put it in a web interface or your computer and use it. That's the next stage.
Fantastic, thank you. Yinting?
Maybe first, Mirona would like to ask a question.
Thank you. Thank you very much, Andrea. That was an excellent presentation. My question is more related to the first question of Katie. Actually, it's like a follow-up. And I was thinking if you have considered, when you are a bit more advanced with the training, to ask from people from the network to send you maybe some images from their labs to see if it performs similarly also. That would be quite interesting,
Yeah.
I think.
And not only that, Mirona, the good thing about that is that when we have all the NDAs ready, we can actually use those images to train as well. So imagine that I'm struggling to have transposition defects. I have Southampton or Leicester saying, well, we have like 200. And if we can use them, it's good because we are bulking in this model, making it better for everyone because we are using more images. And this, if these images work as well as ours, well, we can use them for training, and then we have a better model in the end. So that's definitely the way to go.
That would be fantastic.
Yeah.
Thank you. And Mathieu had a question. He asked, could you detect the metachronal wave or synchrony in the optical flow videos?
Well, I really cannot answer that right now because we are still training with it. But I would say that would be the easiest thing to detect, because when you see the patterns of colors, the more organized the movement is, the more pattern, the better pattern the colors form. So I would say yes, but before starting to jump into conclusions, I need to validate this model that we are now creating with this PCD versus non-PCD, and that will be the next phase. So we need now videos to validate it, to see if the machine is being able to pick up these movements, these specific movements. And we can also use our attention map for that. So if we see a metachronical movement in a specific region, we can see if it's there that the machine is putting its interest or attention or not, if it's somewhere else. So I'm quite, I think it's quite, yes. So I think normal videos will be, normal videos and static videos will be kind of the ones that will be easy. And I hope the other ones will be by defect, that they're not looking normal, and that's how they will be picked up. Like, this doesn't look like the previous one, so it's probably not in this class. So, but machine learning is like, it's neuronal networks, so it can work in so many ways, and we have to analyze the results and build our story based on what we have from our results. So yeah.
Great. Thank you for answering. And Mathieu says, thanks, Andreia, this project is truly exciting. Yes, I think
I know.
this is truly all on our minds. Definitely exciting. No more questions from the audience right now. Please answer, please put them in the chat box. But I have some questions, Andreia. Maybe back to the TEM images. You mentioned that you feed them with at least 600 images, right? And is there some kind of range of pixels where you tell the machine, okay, up to that similarity, it is still fine to make a decision?
Yeah, no, we don't. It's based on your perception. This is one person training it, and that's why in the end it was so important to check with our peers, because you see, I am for a year and then lockdown, so basically me and NOUS together, and no one else was contributing for this training, and I was training it. I don't need to add 600 images. I usually add as much as I can. By the end of having like 1,000, we already had a good performance of the machine, but the more the merrier. So, but the thing is, we cannot ignore the fact that I was training it alone. So I am giving it my own perception of it, what is an abnormality, what is a normal cilia. And I actually did a small survey in the beginning. I asked some colleagues, oh, look at these 10 cilia and tell me about the central pairs. And it was a catastrophe. Like, it was really bad. And I think, oh my goodness, I need to check this in a large scale. I need to check agreement. I need to check if the machine is a mini-me, because I am training it with my own knowledge, and if it actually, my colleagues would agree with the same output. And as I showed you, few, it all went well, because we all have like a 70–75% agreement between each other, us as people, and between us and the machine. And that gives us confidence that the machine is not actually a mini-me, but it's matching everyone's kind of decision or opinion about cilia. So again, to your question, so we don't make any kind of pixel analysis. This is something that I do when I'm training, or when you're training, or when anyone training it, is your perception of what it is, if it's good enough. And that's why I said, if a cilium is good enough for you in your center to do a diagnosis, if you can see the arms and the radial spoke, or see if it's not disarranged or anything, then the machine will be able to read it as well. So it's on your own perception. You don't do any, you might want to just say, oh, this cilia is not good. Just say it's useless, and the machine will put it in kind of that useless basket. This is where sometimes we have kind of that a bit of a gap of accuracy, which is, well, you said it's useless, but actually I don't think it's useless. I could use it. But the other way around can also happen. The machine says, oh, this is totally normal. And I said, well, maybe this is useless. So this is, well, the little tweaks of training come in hand. But this, as I said, little tweaks of training, because in the overall, the project is much bigger than this. The project is trained with much more information than this. So it's, sorry, I think I basically just dragged your question around.
No, that was excellent reply. Yes. Thanks, Andrea. Any other questions? Maybe Katie?
I think you've actually answered all of my questions. I'm just looking at my list.
I can say something that I usually always say, but today I forgot. But I want to say, I want to make this really as a statement. I was doing some academy with some youngsters, 15-year-old. We're talking about AI, and in the end of the day, there was this slight concern that AI might take over, and then jobs, and oh my goodness, what's going to happen? But I just want to say that we couldn't be more far than, like, we're super far than of that. We're not close to any of that. In this case, the machine is great, but the machine can never compete with the creativity, curiosity, and sharpness of the human mind. Because when we look at the patient, we look at the patient with context, and the machine has no context whatsoever. So this is an advantage that we have. When you look at the case in PCD, we look at everything. We don't look at just a single isolated image of the cilium. The same way we don't look at just one video. We look at the patient and all the tests, and even what we know about the patient clinics. So the machine at this point can never do this, and I don't think it will ever be able to do it, because that's not how this machine works. This machine helps us save time with the 10-to-1 normal cases that we have that might steal from us, keep us hostage when we didn't need to be. So we can be more free to be investigating and knowing more about the cases that really matter, and about the cases that are difficult, the cases that sometimes things don't match, but we need to take it to the next level and give it a second opinion. So this is what I wanted to just make really clear. It's really good. I'm super fan of this tool, but I don't think it's going to replace anything. It's really just another team player that will help us do better. Basically, just want to do this final remark.
Thank you very much for explaining that. I'm just going to pop a link to a feedback questionnaire in the chat. This really helps us to shape future sessions. So if you can just spend a couple of minutes filling it out, that would be fantastic. And just to say, our next session is on the 22nd of June, and that's by Dr. Nisreen Ruman, who will be talking about setting up a PCD diagnostic center with limited resources. And thank you so much, Andreia, for your absolutely fantastic talk today.
Thank you for having me. I hope you enjoyed. Yeah, it's very okay.